Thank you very much for inviting me to the 21st EUPVSEC, and many thanks to my co-workers on this paper about module level power electronics. I will start with the principles, talk about measured efficiencies and proposing a new method of shading adaption efficiency, and then I will do an outlook how to proceed further on. Here I show you typically practical PV installation on single-family house rooftops, as I made a photograph last Sunday by bike tour in Switzerland, and you see here these shading situations from a dormer, from a chimney, and here also from a dormer and a small chimney here. And the question is how this shading affects the typical output and performance of these PV systems. From the top view of this PV installation, we take out these three PV modules to demonstrate the principle of MLPEs. And the system is built up by optimizers. These are the DC converters, input output. And you see a second optimizer on the module beside. And what is the benefit of these optimizers? If there is partial shading on this module in the middle, the optimum power could reach at another output current of the module compared to the unshaded module on the right side, where you have, for example, a higher current here. Therefore, the optimizers have the option to find this optimum maximum power point constellation, which could be different from each of the modules. The output of the optimizers are connected into serial, so that at the input stage of the DC-AC inverter will control at a constant 360 volt DC level. And by that way, all of these modules here on the rooftop could be operated in their individual optimum installation and position, where you have an optimum output current of the module. But remember and take care, we have to see that the output current is the same for all these optimizers at the end. Here we will take a closer look at the current voltage characteristic of these 10 PV modules, which are partially shaded by this dormer in the middle. We have to take into account that, for example, if the shade crosses these module number 7, it could be the case that we are crossing here these two different sectors. The sector 1 is controlled by one bypass diode, the middle by the second and the third. So in that case, because this cell is nearly total shaded and there are others which are total shaded, that means the output voltage of that module could have 10 volts less from that sector, 10 volts less from that sector, so that at the end you will not get out 30 volts but only 10 for the optimum condition. And what you see here on the right, you see here dots. Green dot means here that the optimum power of that module, which is correlated to the first one, for example, is at a higher current at 6 amps. So the green dots are always at 6 amps highest power of these individual modules, and we have 4 modules where you see the red dots. And the red dots means the optimum power is reached at smaller output currents of 2 amps. So the optimizers have the option to operate these 4 modules at 2 amps, and the other optimizers operate the other modules, the unshaded modules, at higher amps. But if we compare that with a standard string inverter, The string inverter is only it's only possible to operate it at one certain current, and that would be the higher amps. So the string inverter would have 6 amps. So through all these modules, 6 amps are running. So that means these modules are not operated at the optimum condition, and there we are losing power. And you see that here, that the optimum power for the string inverter is several volts less than in the unshaded condition. So there you see in detail what are the benefits of the module level power electronics in detail. So what's about the efficiency of these DC-DC converters? The datasheet values showing us, for example, here from that manufacturer, 99.5% as a maximum, and they give a weighted efficiency of it's about 1% less. But this weighting efficiency is not the right one, because it's only the same weighting efficiency as for the European or California efficiency, coming only from the irradiance distribution. And we will see at the end of the talk that is not the right weighting factor. 10 years ago, colleague Roland Bründlinger from Vienna also did measurements on these DC-DC converters. At that time, the datasheet values were about 1% less, but where they are today. And to answer these questions, we measured in our lab 10 optimizers which are connected into serial in our lab system, and each of the optimizers are powered by a DC power source, which are emulating the EV curve of the different modules. So, for example, module 5, we could implement a shading case where module 8, for example, is unshaded, and then we power these other optimizers by a different EV characteristic. And therefore, we could measure over a whole day for all the situations how the shading is changing, average efficiency, and the average efficiency you find here on the left side. So the rated power is on the right side. So we see efficiency values between 98%, which is 1.5% lower than the maximum datasheet efficiency, and also much lower than the weighted efficiency, and the efficiency goes down even to 96% for the system. So what is at the end the real efficiency? And to answer that, we started with implementing a first loss model, as you see it here. And we propose a simple formula where you see the ohmic losses are proportional to the current square, and these are switching losses and constant losses here. But to get out such clear loss power versus input current of the optimizers, you have to select only these measurement points with a certain input voltage, and that's for 27 volt, that's for 32, and that's for 38. So at the end, these coefficients C0, 1, and C2, we can make a polynomial which is a function of the input voltage, and then we have a first loss model of the DC-DC inverter, which only is working for the buck mode, so where the output voltage of the inverter is smaller than the input voltage. But how this looks for the whole range, and the whole range of these MLPEs is showing here, because you see here the efficiency. The datasheet value of 99.5% is not reached, but a little bit lower than that. But that is reached only at a input-output voltage ratio of 0, close to unity. But in reality, this is not reached. So in reality, we have different conditions for the different optimizers, and it depends strongly on the number of optimizers which are connected into a string for the unshaded mode. So it is highly important if, for example, the modules here, the optimizers have to operate so that the output voltage is always nearly half the input voltage, which is the case if you are choosing as a designer the maximum number of optimizers in your string. And there you have maybe 1.5 up to 2% less power compared if your design would show up with a unity input-output voltage ratio in the unshaded mode for the optimizers. These values are not given from the manufacturers, but they are highly needed for the people out there, for the practical guys, to design an optimum system. And therefore, you see here the whole operating area of an optimizer. For example, here on the right side, you see the situation where the ratio input-output is higher than 1 and here lower. You see the maximum efficiency is reached close to 1, so input-output is 1, and you are at about 10% of nominal power. If you have input-output 1 and you increase the power, you see here the ohmic losses of these DC-DC converter, and you end up with about 1 or 2% less power at nominal output condition in the best case. In the other case, you can have 2% less efficiency at high energy values of the DC-DC optimizers. And the manufacturers, again, didn't show us these data and this efficiency, and therefore we think we have to try to get more information, also to test it and measure these optimizers at other labs as well. And at the end, but how we will reach the people out there, the practical guys. Therefore, we propose a simple number, shading adaption efficiency, which we will see at the end on the datasheet of an optimizer, and which is related to a certain shading condition, for example, such as a chimney in the middle, which shades the PV module 11 and 7, for example. And here there is another time during the day where the shade reaches module number 12. If you compare these, this is the power, how it increases over the day. Here at noon you have maximum power, and you see the red and the blue lines. The red line means that here the optimizers will find the optimum power, and on the left side here the optimizer find the same optimum power than the string inverter, and in that case we don't need an optimizer for that condition, but in that case we need it. So because that is changing over the minutes and hours during the day, we did this mapping in the right side of the graph here, and there you see the difference between the performance of the MLPE systems relative to the standard string inverter. And red means, here the red area means we have less power coming from the optimizers, and blue in the morning, for example, at 9, where we have less power, there we have, blue means a gain of energy from the MLPEs in the morning, and at noon we have less powers from the optimizer. And the reason for that is simple, because we have, for example, 10 small power DC-DC converters. They are not operating in such a high efficiency area like if we have one high power DC-DC converter, as it is the case in a standard string inverter. And our method we want to propose is a simple one, and it's similar to the average efficiency, the European and the California for the standard inverter. We will propose, for example, 6 typical conditions for the different colors, and we will measure, for example, operating point 5 in the lab, and out from that efficiency we have a weighting factor, and with that weighting factor, which covers all the losses over the whole year, we will be able to measure an individual power electronics, for example MLPE, but we can also measure a standard string inverter at these 6 different operating points, and with the measured total efficiency multiplied by the weighting factor and sum that up, we will end up in an average annual shading adaption efficiency. And that could look like that. Here on the left side, that's the efficiency map of the MLPEs, and on the right side with the same shading conditions for the same partial shaded modules for these 6 typical operating points, we will end up, and these curves look similar, but they are not similar. And the difference you saw in the graph before, which is only in a small percentage of efficiency. Here on the bottom of the results, you see the MLPE system have 96.6%, which is in favor of about 1.2% relative to the standard, the case 2, the standard string inverter system. So at the end, for the annual efficiency, the efficiency is only in the range of 1 or 2 or 3% difference. But we will see on the next slide that is related to the costs and prices for the power electronics, even if that is only 1%. But what are the other results I just showed before? We need for the design phase, we should tell the people out there, please try to get unity between input and output for the unshaded mode. If you are using Optimzer, and don't take the whole range, because then you will lose an efficiency. And for example, doubling the number of MLPEs, you will lose 1.5% efficiency. And we propose this method, which ends up with a shading adaption efficiency. And at the end, the outlook shows us that the economics is relevant, and we learned that from the DC voltage dependency of these standard string inverters. 1% gain in efficiency due to the use of another power electronics will increase the price of that power electronics by 10%, because the share on the total system price is only 1/10. And if we take into account that today 20 gigawatt PV systems are operated by MLPEs, we talk about $200 million, which are related to that gain of 1% or lose of 1%. So outlook is we have to tell the people out there, the practical guys who are designing the system, the small system, try to take unity for input-output, not take the whole range of optimizers which are possible to operate, so that the system is functioning, operated as in an efficient mode. And the second thing, because it is not possible that each of the installers invest a lot of manpower to make a 3-dimensional geometry measurement of the dorm or of the chimney, and in detail in a centimeter scale on the whole roof, and therefore we propose these for typical shading conditions, a datasheet value which the manufacturers should show in their datasheet in the same way than the standard inverter efficiency manufacturers show the European and the California efficiency. That, in our opinion, is the simplest and real practical solution not ending up with a very complicated simulation tool for each small single family house system. That will not work on the market. And to further develop that, we have to develop standards. And we talked to the ISC task 82, and they are interested, and we will start a collaboration within the International Energy Agency PVPS task 13 together with other labs to exchange our thoughts, and at the end to have a method where we could measure different devices by same method in different independent labs so that the customer are convinced that efficiency could be optimized. So with that outlook, we would also appreciate if we could get your information and your feedback, if you have also experience, and give us also your thoughts about these power, efficiency and performance of the MLPEs. So again, thank you for your attention.